Students often ask, what's the point of higher order functions? Make adder is cute, but why don't we just add x and y directly instead of building a higher order function? So I've constructed a slightly longer example that tries to illustrate why you might want to define a bunch of functions and work in the space of functions until the very end of the program. And the example is generating sounds. So what we're going to do is write down a wave file. That's a standard format for encoding sounds. It's not used much these days because it takes a lot of space. It's a really simple format that doesn't involve any compression at all. But it's really simple to generate a wave file, so that's why we'll use it. All a wave file does is encode samples of a sound wave directly. Sound comes in waves. The wave has amplitudes at any moment. And what sampling does is allow us to digitize this wave by just recording the height or amplitude of the wave at particular moments. So that's what these dots are. Thanks Wikipedia for this cool picture. So the wave itself looks like this. We take lots of samples at particular moments in time, and we're going to take, for example, 11,000 different samples every minute in order to get as close an approximation to this structure of this wave as we need so that it sounds cool to the human ear. And usually these waves are created by recording sounds in the real world. But you can also generate waves from scratch according to mathematical functions. And there are several standard simple waves, one of which is called the triangle wave. So there's a sine wave that you can generate mathematically, or a square wave, or a triangle, or a sawtooth wave. All of these are used in various forms of electronic music. I think the triangle wave sounds better than the other three, so that's why we're going to use it in this demo. Since this example is a little longer than usual, I'm not going to type out every line, but I'll show you what I've done. I've used some of the built-in modules in Python in order to construct the wave file. There's a whole module about waves. You can read about it. There's a module about encoding integers in the format that wave files require. That's called struct. And then we'll need the floor function, which takes a number and rounds it to the greatest integer that's less than that value. Now we pick a frame rate. That's the sampling rate. How many times per second do we want to have some value that tells us how high or low is the waveform of the sound? And here's the part that I don't think you should read. You're welcome to. Here's how you encode a value according to what the wave file requires. You can read about how this works on the Python docs, but just trust me that this is one way to get the value you need. And here's the function that actually writes the wave file. So we pick some name for the file. The standard way to write this is some name .wav. We pick the length of the sound that we're generating, and then we have a function that's going to describe the waveform for the song that we're trying to generate. And this is the function that we're going to write later. Whatever this function is, it's a function of t, the time into the song that has elapsed so far. So we start out at the beginning of the song, and then we go through all of the t's that are the number of seconds in the song times the frame rate. So we're going to do 22,000 times call our waveform sampler on t. And then we'll write that out to the file in order to generate the wave file that our computer will actually be able to play. So sampler is some function that we're going to need to generate that gives us numbers between -1 and 1 and describes the samples of the wave. So if we were trying to generate this sound, then the sampler would have to give us 0, and then a half, and then 1, and then 3/4, and then it's about a half again, and then 2/3, or whatever these values are at each sampling point. Now, how do you come up with the samples for a triangle wave? Well, you have to know the frequency of the wave. That determines the pitch. And the amplitude, that determines the volume. And then there's this fairly straightforward equation, which is that you figure out how many time steps are required before the triangle wave repeats. So in order to draw one triangle shape, like that. Once you have the period, then you can write down a function that takes in the value t, builds a saw wave, computes the absolute value of the saw wave, multiplies by the amplitude, and then you have a triangle wave. And one more line I'll add here is that the frequency for the note C is 261.63. That's just a fact about how instruments are tuned in the modern world. Okay, let's see what happens when I create a triangle wave at the frequency of C. Let's set t equal to 0. While it's the case that t is less than 100, I'm going to print out what I get when I call C on t, and then I'm going to increase t by 1, and we'll see the shape of the triangle wave. Okay, so it starts out at negative 0.3, because that's my amplitude, works its way up to 0, and then all the way up to positive 0.3, then works its way down to negative 0.3, then it works its way up to positive 0.3. That's our triangle wave. If we play C, what I've done now is write a file. I'm going to open it up using my operating system. Here's the file, song.wave, and if I play it, I heard a triangle wave for C. Okay, so things are getting interesting. Now I can play a sound. And the sound just sounds like a flat tone, but that's something I can work with. I can take a function, like what comes out from try, and combine it with other functions in order to make music. So next, let's write down the frequencies for 3 different notes, C, E, and G together. And what would it mean to play 2 at the same time? Well, I'd need a function that plays both, some F and some G, which are both functions. And that's a function of t that just returns f of t plus g of t. Now I think I can construct a 2-note chord just by playing both a triangle wave at C's frequency and a triangle wave at E's frequency. Don't forget to return a function, and then we'll run our code and hear what we got. A C and an E together. Let's add some rhythm. I'm going to define a function that takes in some particular sound, F, and only plays it from start to end, where start and end are measured in seconds. To do that, I need to create a new function, a sampler function that first expresses t in seconds. That's t divided by the frame rate. Then checks to see whether those seconds are between start and end. If seconds are less than start, return 0. If seconds are greater than end, return 0. Otherwise, just play the sound. And the sound in this case is a function where we just call that function on t in order to get it to play. So let's create C and E as triangle waves at C frequency and E frequency. And we can play a note. The C note from the beginning, and let's make it a quarter note. All right, mostly silence with a little beep at the beginning. And what if we want 2 beeps? Well, then we'd play both the C, which is a quarter note at the beginning, and an E, which is starts after a half a second and lasts for a half a second. I run my code again and listen to the song. Now we're getting somewhere. But notice it sounded a little harsh at the beginning and end of each note. Almost a little scratchy. I don't know if that comes through in the video, but it's an important part of making music that you make each note sound right. The way we'll fix that is just to add a little fade at the beginning and the end. Just for 1/100th of a second. We'll have the amplitude increase and then decrease. So if it's the case that seconds is less than start plus the fade in time, Then what we're going to do is compute the difference between seconds and the start. So that's how far into the sound we're in. And we'll divide by the fade length to get a percentage of the fade. And we'll multiply that by f of t. If it's time to fade out, that's when seconds is greater than end minus the fade. We can figure out how much is left. End minus seconds. Divide that by the fade time, and multiply by the amplitude. So that means we'll fade in, and then we'll fade back out. In order to hear the effect, maybe we'll make our fade length a little bit longer. How about 0.1 seconds? But to make it sound as natural as possible, we'll do a really short fade. So it's like the note is starting up right away, but we don't get any weird artifacts in the sound. 2 nice clean beeps. Let's add some more. I'm going to keep track of how far we are into the song, starting with 0. My first note will be, starting right there at C, I'll play an E. And I'll play it for just 1/8 of a second. OK, now I'll move forward in time by 1/8 of a second. And then I'll keep the song that I have already and add another note. How about another E, starting where I am now? This time it's an 1/8 note, but after it, I'm not going to play another note for 1/4 of a second. That means I have an 1/8 note followed by an 1/8 rest. I'll do that again, and then have an 1/8 note that has no rest after it, and now I think it's time for another note. And let's make this one a C followed by an E. So how much time have we used up in total? Well, there's 3/4 and 2 more 1/8 makes a whole second. We have 2 seconds according to the length of the song that we defined in the beginning. So let's add a couple more notes. How about a G for 1/4 and have a little bit of rest after that? And then another G, but this time let's make a low G. The way you reach a low G is just to divide the frequency in half. So I'll make a triangle wave for G's frequency, and then a triangle wave for G's frequency divided by 2. And instead of playing these 2 notes, we're going to play our whole song. All right. So we have the beginning of the Mario theme, just as 1 note at a time. But remember, we could play chords. Here's a way to make chords. I'm going to put all of this into a function. The Mario function needs to know which C, E, G, and low G it's going to use. And then it will return the song that's generated. Instead of committing to a particular C, E, G, and low G, we'll play Mario at a particular octave. And the way you set the octave is just to multiply the octave by the frequency. So if the octave says go 1 octave above, we'll write that as 2, which multiplies all the frequencies by 2. Or if we want to drop an octave, then we'll just divide by 2, or multiply by 1/2. So how do we make a song? Well, we have local names C, E, G, and low G. We'll call Mario on those, which might be different depending on what octave was passed in. And now we can play Mario at different octaves. Mario at 1 is what we heard before. Mario at 1/2 plays it an octave down. And of course, since we're representing these as functions and we can combine functions in any way we want, we could play both Mario at 1 and Mario at 1/2 together. And that's how you make music using a computer. All by defining functions, building some elaborate function built out of both and try, combined together in lots of interesting ways, and then we pass that function into play, and it just calls that function on every value of t, writes out the result to a file, and that's how we have a song.